I'll take it to an Ivy League school. Won't get hollow.
Calculator on them? Do you have one? Can I borrow it for the last maybe 5? Do you need it during the tutorial? Or? Oh, not? Can I borrow it? What's your name? Rose? Thank you, Rose. All right. All right. How's it going? All right, let's get started. Let's get started. So how's everyone doing today? We feeling good? What, maybe we're feeling a little bit nervous for our test on Monday? How are we all doing? Let's get started. Let's get some energy. How are we all doing today? That's much better. I'm very glad to hear. So first things first, well, let's get some stuff out of the way. I want to cover some more integration techniques, more substitutions, more ways that we can do things quickly so that we can optimize for our test. I want to show you another trick on our calculators before the end of the tutorial today. I also had some questions about test review. I'm working on, right now, making just a video like going over the solutions for the test for 2024. Is that something that you guys would want to see? Yeah. Would you prefer to do that as the tutorial, or would you rather do the other stuff that I've prepared and then you can just watch the test as a video? Is that better? Is that good? All right, let's do that. Let's do that, shall we? So yeah, I think that is everything out of the way. So let's get started. So let's let f of x be equal to the sine of x. And we're going to ask, where does the function g of x attain a maximum on the interval 0 to 2 pi? Oh, also, by the way, we're still going to be doing a mix of like test review content for this tutorial, but these questions might not be the same difficulty as the ones you're going to see on the test, OK? So we're going to still cover all of the content today, but yes, go ahead.
Sorry, does that mean the questions here will be easier or what?
Some might be easier, some might be harder. These are not designed to be representative of the difficulty, but that's a good question. So where does the function g of x attain a maximum on the interval 0 to 2 pi? So the way we can find it is, remember, g of x attains a maximum when its derivative is 0 or its derivative is going to be undefined. So it's going to attain a maximum on a critical point or at a boundary point of this interval. So in order to do that, let's first find g prime of x to look for the critical points. So g prime of x is going to be the derivative of the integral of from 0 to x of f of t dt. And by our fundamental theorem of calculus part 1, we know that this is just going to be equal to f of x. So the derivative of the integral from a constant up to the upper bound being the variable x is just simply f of x. So that's our fundamental, bless you, that's our fundamental theorem 1 right there. So in order to find the critical points, we want g prime of x to be either 0 or undefined. Now f of x is sine of x, right? So g prime of x is going to be 0 at the points when sine of x is equal to 0. So sine of x being 0 happen at multiples of pi, integer multiples of pi. So on the interval 0 to 2 pi, that means we're going to have 0, pi, and 2 pi as our values. Those are going to be the critical numbers. Are there any places where g prime is undefined? Are there any points? No, there's no points. Yes, there are some points. No, because sine of x is a continuous function, but we should make sure still that we're checking, at least in our head. We can also notice that these 0 and 2 pi interlap with our boundary, so we don't have to check our boundary. So these overlap with our boundary here. All we have to do now is plug in and find g at those values. Now, okay, there's, I guess, a number of different ways we could do this. In order to get practice with our anti-differentiation, maybe let's actually just come up with an explicit expression for g. So g of x is going to be equal to the integral from 0 to x of sine of t dt. Integrating sine, that gives us negative cosine of t, evaluated at 0 to x by our fundamental theorem of calculus number 2, which is going to give us negative cosine of x plus cosine of 0, which is 1. So if we evaluate this g of x at each of these points, g at 0 is just going to be equal to negative 1 plus 1, which is equal to 0. G at pi is going to give us negative cos of pi. And remember, cos of pi is going to be exactly half a period, so we're going to be at negative 1. So negative 1 plus 1, which is 2. And then g at 2 pi is going to be the same as g at 0 from the periodicity. So g at 2 pi is just going to be equal to 0 again. Okay, so yeah, any questions about this one? So, oh, and the maximum is attained here. So this integral is going to be giving us the area. So actually, maybe let's just look at it geometrically here as well. The area from here under our sine x curve, that means if we're looking for the maximum area geometrically and we want to find, okay, over what period do we accumulate the most area, here we're going to be accumulating positive area. This is pi, and if we were to go any further, now we're accumulating negative area. So if we want to think geometrically, where is our integral achieving the maximum area, we want to go all the way up until we're hitting those negative values in which we're going to start accumulating negative area. And then geometrically, g of 2 pi is going to be 0. Notice by the time we accumulate area all the way up to 2 pi, all of our positive area is going to have canceled out with all of our negative area. Cool, so I think this is a nice kind of geometric intuition for this one. What questions do we have? Okay, let's go back to some differential calculus, because it's been a while and there will still be some differential calculus on the test. So let's talk about this one. Which of the following is true? E to the x is bigger, equal, or less than 1 plus x for every value of x. Or it's none of the above. I'm going to let you think about this one. Let's take 30 seconds to just feel which one feels true. And then we'll talk together. So everyone discuss with a neighbor. Oh. What feels true? A? Why? Do we have an argument?
E to the 0 is 1, and then 1 plus 0 is 1. Then e to the 1 is 2.7, then 1 plus 1 is 2.
So you plugged in points to find that.
Pretty much.
Ah, but we're saying for every x. So what if there's a value of x where it doesn't work? Is there any algebra, any calculus we can use to prove that one? Okay, let's talk about some things. So I asked one of your colleagues here who had suggested, oh, let's try plugging in points. So okay, yes, any points if we try plugging in, yes, it's going to give us values that are bigger than 1 plus x. But I said for every x. So maybe there's a point x that you didn't plug in where the inequality doesn't hold. So okay, first off, let's try and vote. Who thinks it's A? Okay, almost everyone. Who doesn't think it's A? Okay, so I'll tell you already it's A. So let's try and, for the most part now, try and work on showing why it's the case that it's A. So what ideas might we have for the people who said A? Why do we think e to the x is always bigger than 1 plus x? Yeah.
Well, C can't be true as soon as you start getting to larger numbers, and it also can't be true because 1 plus x can be negative, but e to the x can never be negative.
I see. Okay, very good. So that's a good argument there. It's kind of some intuition. We're looking at counterexamples for C. So for example, they said if we plug in negative x, the right-hand side is negative, but this is always positive. So we've eliminated C. My question is, why is A correct? Why couldn't it be, well, I guess it can't be B either because it's not going to be equal, but yes.
Because every time you add 1, you're multiplying e to the x. Like you're multiplying by e every time you add 1. So if you have like x is, suppose like x is 2, you have 3 on one side, but then you have e squared.
Okay, that's reasonable. We're still thinking about it very intuitively or very mathematically, as if we were like a calculator. I want to think about it using tools like in calculus. So here, I gave this hint. Does anyone know what the tangent line to e to the x is? Let's say at the point x is equal to 0. What's the tangent line? The tangent line. So we just want it in the form of mx plus b. So what is the tangent line? Yeah. Yeah, it's 1 plus x. The tangent line, so at x is equal to 0, the tangent line is y is equal to 1 plus x. And we could find that by using our tangent line formula from before. Now the next thing is, let's take the second derivative of e to the x. So let f of x be equal to e to the x. The second derivative of f is still e to the x. And the second derivative here is always positive because the exponential is positive. Okay, so we know our second derivative is positive. We know what the tangent line is. Does anyone remember what's the geometric intuition behind the second derivative being positive? It's a word that starts with a C. Yeah. Yes, concavity. We know that our function's concave up. And if our function's concave up, geometrically, we know that it lies above the tangent line. So our function is concave up, which means that it lies above the tangent line. So we know that e to the x is always bigger than 1 plus x. So what questions do we have about this one? So here we're using our calculus to help us find this value. We're using the concavity of the function. We know it's concave up everywhere, so it's going to lie above that tangent line everywhere. Yes?
Perhaps an alternative way to solve it, because if you think about both of these functions visually,
Yes, absolutely. And that is exactly what our concavity is telling us. It's the rate at which our function increases. It's the derivative of the derivative. So absolutely, our function is going to curve upwards. Thank you. So let's keep going. Let's keep moving. Let's keep pivoting. Questions are in random order. Let's do an integral. So who knows? So we have the integral from -1 to 1 of x to the 5 over 3 minus x squared cos of x dx. Take another maybe 15 seconds to solve this one. Emily, I know you know this one. Anyone have any ideas for techniques we might use for this one? You have an idea?
I'm thinking it's maybe, what's it called? Symmetric function? Which one? I don't know which one is the one which like equals 0. Because I kind of don't want to do the work first after that one.
We'll see. Yes? By induction? No. Induction would require us to have a set that is a well order, right? But if we're looking over the set of all possible x values, which is the reals, that's uncountable. Where have you heard induction? Ah, very good. So you'll see that next semester, but definitely it won't work for this because we have an uncountable set. So we can look at other proof techniques as well. Okay, let's discuss. So what techniques could we use for this one? Yeah. I'm sorry? U substitution. Okay, what value of u might you choose for this one? If we choose a value for u like 3 minus x squared, after we take the derivative on this, you're saying we're going to get a derivative of x, right? Or some multiple of x. It'll be negative 2x. If we have to sub that back inside the cosine, it's going to get really messy. So you could try it. I'm not sure if it would work out, but there is a way that I think we could do this one much faster. What else do we think? Yeah?
Is it an odd function?
Well, let's try and prove that. Why do you think it's an odd function? So yes, we have an x to the 5. Okay, so let's remind ourselves. So an odd function is one that satisfies f of x is equal to negative f of negative x. This is an odd function. What this means is that we get rotational symmetry about the origin when we plot the graph. Notice our x to the 5, that's an odd function. It's a polynomial of only odd powers. We're dividing it by 3 minus x squared, which is an even function. So we have an odd function divided by an even, and then times an even. So this odd divided by even is still going to be odd, and then odd times even is still going to be odd. So here, this function is the integral of, from -1 to 1 of an odd function. So notice we have a symmetric region. So all of our positive area on one side is going to cancel with all of our negative area on the other. Our function is going to be symmetric about that origin. All of the areas are going to cancel with each other. So what's the answer? 0. So if you see an odd function on a symmetric domain, don't try and compute the integral.
So, you said the odd divided by even is equal to odd.
Yes.
And the odd times even also equal to odd.
Yes.
And how about even over odd?
So, okay. So I think one thing is we might be confused about, okay, how do we know that our functions are odd or even? Let's say we don't remember the rules. Oh, odd divided by even divided by odd. What I would suggest is plug in negative x into our formula here, and we'll see if we get, like, into the function itself, and see if we get a negative value for f. So here, if f of x, so let's actually just verify. If f of x is equal to x to the 5 over 3 minus x squared cos of x, then f of negative x is equal to negative x to the power of 5 over 3 minus negative x squared cosine of negative x. So here in the numerator, we can pull out the x, the negative 1 power outside of the 5 because it's an odd degree. So we have negative x to the 5. When we have a square, negative inside the square does nothing because a square is even function. It's symmetric about the y-axis, x squared, and cosine is also even and symmetric against about the y-axis. So this gives us negative f of x. So if in doubt, always just plug in negative x into your function and see what pops out.
Oh, okay.
Does that answer your question?
Yeah.
Yes, very good. All right. Oh, yes, question. What if it wasn't over a symmetric interval? Then we can't apply this technique. So maybe you might not get this type of question. Maybe you'll get another integral that would be easier to solve. Yeah. In general, has anyone picked up that we call our integration techniques techniques, and we call the derivative rules rules? For derivatives, they always work. We can follow kind of an algorithm, a set of rules. For this type of problem, we don't always have a set of rules that will work. That's why we call them integration techniques. Let's keep going. Let f be equal to ax minus x cubed. For which value of a does f have 0 critical points, 1 critical point, and 1 inflection point? Aha, this one's fun. OK, why don't we take, I'll give you a minute. Let's take a minute to solve this one. Just kind of as a disclaimer, I made a mistake in one of the questions for the test 2, like the video that I made, and I don't really have time to refilm it, so I'm just gonna post it. But it's you know the definite integral one where you have to compute it from like 0 to 6. So I did it on the entire graph. I computed it from 0 to 12, and I was just like mindlessly adding like, oh, here's a rectangle, here's a square, or whatever. So just keep in mind that it's wrong. All right, so let's take a look at this one. So in order to find the critical points here, what we need to do is we need to take the derivative. So the derivative of f is going to be f prime is equal to a minus 3x squared. Now, to find the critical points, we want this derivative to either equal 0 or want it to not exist. Notice that the derivative is a polynomial function. It's going to exist everywhere. So in order for this to be equal to 0, we just need x to be equal to a over 3 all rooted, plus minus. OK, now this number exists if a is bigger than 0. So if we want 0 critical points, then we need this number to basically not exist. So for 0 critical points, 0 critical numbers if a is less than 0, and we have exactly 1 critical point if a is equal to 0. So 1 critical number if a is equal to 0. Or yeah, equal to 0. So note if a is equal to 0, then the only critical number is x is equal to 0. If a is less than 0, this root is not possible. Bless you. So this is our answer for a and b. The next question says, for which value of a does f have one inflection point? In order to find the inflection points, we should check the second derivative. F double prime of x is equal to negative 6x. And actually, you'll notice that what happens to our a term? Our a term goes away, it disappears. So actually, the presence of the inflection point is not determined by the value a. Here's another interesting fact. A cubic function will always have one inflection point. If you check the concavity, will always have one inflection point. And did you know that if you, let's say you moved the inflection point of a cubic onto the origin, the cubic function is always odd around the origin. It always has rotational symmetry around its inflection point. So even if your cubic is not centered at the origin, there's always rotational symmetry around that inflection point.
So A just disappears.
Yeah, a disappears. So it's not determined by a, so this holds for every value of a. So for any a, there's always one inflection point. I'm putting together, hopefully this is helpful, I'm putting together a list of practice problems for studying for the final as well, which are more difficult than the ones that you'll see like in the, I don't know, in your textbook or other stuff like that. So hopefully that's helpful as well. And this type of problem is going to be in there. So showing that cubics have rotational symmetry around the inflection point. It's very cool. All right, let's keep going. This is stuff, let's skip over these ones. I put them in there anyways if you want to take a look. More integrals. Let's let a and b be positive numbers with a less than b. Suppose that the integral from negative a to a of e to the negative x squared dx is equal to c. Suppose that the integral from 0 to b of e to the negative x squared dx is equal to d. We want to compute the integral from a to b. What is it? Sorry? A minus a? Where are we doing a minus a? So here, so a is a positive number. A could be like 1, it could be like 5, it could be like anything. So the key to notice is, let's draw this function here. So this is 0. We have a number a right here. We have a number b right here. We want the integral over this region. But we don't have that yet. What we do have is an expression for this integral here. And we have an expression for this integral here. So what we could do, how do we get the yellow highlighted region? Let's take the green region here and subtract the interval from 0 to a. So we're going to use a couple tricks. The first thing we're going to use is the fact that this function has even symmetry. So this function here, if we let f of x equal to e to the negative x squared, f is even. So in that case, c is equal to, let's do it like this. The integral from 0 to a of f of x dx is equal to 1/2 the integral from negative a to a of f of x dx. So this is by even symmetry. And this is equal to 1/2 of c. So we're just plugging in the value c from our question. Now similarly, we know the integral from 0 to b is d. So in order to compute this final value, we'll notice that this is just the integral from 0 to b of f of x dx minus the integral from 0 to a of f of x dx. So the integral from a to b is just the integral from 0 to b minus the integral from 0 to a. So from here, this is going to give us d minus c over 2. And that is our final answer. So here we're using the even symmetry of our function over a symmetric interval to find that the integral from 0 to a is 1/2 the integral from negative a to a. We used that expression and subtracted it from the integral from 0 to b in order to find the integral from a to b. What questions do we have about this one? Yes? Yes. The 1/2 came from the fact that, so you see the interval from 0 to a, that's 1/2 the distance from negative a to a. Because it's even. All right, let's get into some more integral computations. So let's just do a couple back to back. So let's evaluate this integral, product of x and then x minus 1 to the power of 4. What's tricky here is the fact that our x minus 1 is to the power of 4. Notice if we were to do a u sub, if we set u equal to x minus 1, then our x is going to turn into a u plus 1. So then we can easily expand. So notice if we set u equal to x minus 1, then that means that x is equal to u plus 1. And also taking the derivative, we get du is equal to dx. So now we can sub in each of these ingredients. This is the integral of u plus 1 times u to the 4 times du. Notice we subbed in every single possible value. Now you're going to say it looks very similar, and it does. But now notice that we've moved the plus 1, or the plus a constant, over to the term with just a power of 1, to the factor of a power of 1. So now we can easily expand this, turn this into a standard form for our polynomial, u to the 5 plus u to the 4 du. And now we can integrate using our power rule. 1/6 u to the 6 plus 1/5 u to the 5. Don't forget the plus c. And we can now just substitute back to get our final answer of 1/6 x minus 1 to the 6 plus 1/5 x minus 1 to the power 5 plus c. And that's the final answer. What questions do we have about this one? Yes? That's a good question. So let me go through our reasoning one more time. We saw that this is a polynomial function, right? It's in factored form, but it's a polynomial function, which means we should be able to easily compute its antiderivative. What's tricky is the fact that we have the power of 4 on that x minus 1. If I wanted to expand it out, I would need to expand out a power of 4, which is very tricky. So instead, we're using a u sub to move that power of 4 to have the u term with no translation. So if we set u is equal to x minus 1, we'll notice we're going to get the same polynomial, and we're going to have the same du as well. We're not stretching our space at all. We're just translating our function over, and then we can expand out the u minus 1, or u plus 1, excuse me, into our power of 4. Does that make sense? Okay. All right, let's try another one. Let's keep going. So let us compute the integral of 1 over 1 plus sine of x. You can take 30 seconds to do this one. What are we trying for this one? Can I see? No? It's okay. No? Can I see?
Oh, I have not.
Oh, I haven't started? That's okay. What do we got for this one?
I thought I'm doing substitution, but I'm not.
Hmm.
Yeah.
No, it's
Hey. What does 1 over sine look like? I actually don't know. I'm not sure. Nice drawing. What is it? Nice. Sorry? All right, what ideas do we have for this one? What ideas? Yes? Let's sine of x equal u. So if we set sine of x equal to u, then when we find du, we're going to need a cosine of x. Where does the cosine of x come in? So maybe we can't set u equal to sine of x. I like where we're going. Yes? Sorry? Yes, absolutely. You multiply by the conjugate on this one. I wanted to be tricky because with this one because in last tutorial we had like 1 over 1 plus e to the x and you had to add and subtract 1. For this one, if you were to add and subtract, it wouldn't work because you would get a negative sine x over 1 plus sine of x, which you still can't use sub. So this one you get by multiplying by the conjugate. If you multiply by the conjugate, the integrand turns into 1 minus sine of x in the numerator, 1 minus sine squared of x in the denominator. What's 1 minus sine squared of x? That's, yeah, cosine squared of x. So this is the integral of 1 minus sine of x over cosine squared of x dx. So this is, let's separate this into two parts, secant squared of x minus tan x secant of x dx. So then what's this? Integral of secant squared of x is just tangent of x. And then integral of tan x secant of x is just secant of x. And don't forget to add the plus c. Everyone happy with this one? So we should remember, multiplying by the conjugate is always a way that we can go back and do it. I'd also like to pause and say, I really appreciate that everyone jumped in and was trying a bunch of different integral techniques. Because when we're on a test, there is no consistent way that we can just find and compute our integrals. The only way we're going to be able to do it is continue to try as many things as we can, and we just hope that the first thing that we try is also the one that gives us the correct answer. What questions do we have? What questions do we have? Sorry? What did you say? You went like this. No? Nothing? Okay. Yes? Yes. From the second last step to the last step, we just used our antiderivative formulas. It's the same thing as we knew from before, derivative of tan x is secant squared, etc. Yes, Ava.
How are you able to identify when it's going to be more useful to multiply by the conjugate?
How do we identify that we should multiply by the conjugate here? So this we should think back to our rules from our limit calculations when we also often multiply by the conjugate. We see that we have a 1 plus sine of x. We know that if we multiply by the conjugate, we're going to be able to simplify that denominator using our cosine squared of x. So I guess kind of just seeing that we're going to use trig identities in the denominator, that's how we can kind of take a look. Okay, let's keep going. Integral of x squared over 1 minus x to the 6th. Do you want to take another 30 seconds? Actually, let me just look at what else we're doing today. Okay, yeah, we're doing good on time. What do we have on this one? Dia, how's it going? It's going? Can I see?
So far I have written out the first top. Honestly, my biggest issue with integration is just knowing, like, there's no, like, I feel like almost ideal flowchart, but I feel like that's not even possible.
That is everyone's difficulty with
Like, I
integration.
feel like there's no sequential, like, it's kind of just, I think eventually I have to notice patterns. But, like, I have 3 days to notice those patterns.
It's okay. We'll make good use of those 3 days. Yes?
What do you usually, like, what's usually going through your mind when you're trying to choose when or when not to use something?
You're looking for, okay, the question was, what's going through your mind when you decide whether to use u sub or not? The trick is, you should look for a function whose derivative appears in the integrand. So if we're trying a u sub here, not that it's necessarily the approach, can we find a function whose derivative is in this integrand? That's what we're looking for. Does that help? Yeah, go ahead.
Yeah, so if you just look for the integral for the derivative of the entire thing, if you can't find that, should you just immediately know not to do so that it wouldn't work?
You might have to do something a little clever. So we'll see an example here. Yes?
Could you consider the difference in cubes instead of root? Is that too much?
You're on the right track, but that's not what I did. You're on the right track, though. I like where you're going with this. Okay, let's give it a try. Let's do it, shall we? So, did anyone come up with a substitution that works for this one? Or I mean, a technique that works for this one. I might have just spoiled that. Yes? Sorry? U is equal to x cubed. How did you know that was the correct solution? Very good. So, if we set u equals to x cubed, so let's rewrite this in a couple ways first. So, let's rewrite this x to the 6 as x cubed squared. So now, if we set u equal to x cubed, then notice the derivative of x cubed, which is a factor of x squared, a factor times x squared, that appears in the numerator. So the trick for this one is you have to see, okay, we have an x squared in that numerator. Can we find a function whose derivative is x squared? And x cubed works. So if we set u equal to x cubed, then we have du is equal to 3x squared dx. So 1/3 du is equal to x squared dx. So now we can sub this and sub this back into our integral. So this gives us the integral of 1/3 du. We have 1 in our numerator, and then we have this root of 1 minus u squared. Does the different colors kind of help out and see where our substitutions are coming in? Okay. So from here, now we can integrate this one really easy. What's this? What's this? Yeah. Yeah. Arcsine, yes. This is the integral of arcsine. Or sorry, the integral of this is arcsine. I misspoke. This is 1/3 arcsine of u plus c. So we can now substitute our formula for u back in here. So this is 1/3 arcsine of u plus c. So is everyone happy with this computation, how we chose our correct u and how we substituted that back in? Yes? How did we figure out how to make x to the 6 x cubed squared? So the way we figured this one out is we are searching for a function whose derivative appears in the numerator. So you see we have an x squared in the numerator. We're looking to make a substitution whose derivative is x squared. So which function has a derivative of x squared? A multiple of x cubed, right? All right. So we're actually getting a little bit close to time. So let's keep, is it okay if we keep moving, or does anyone have a question? Yeah, go ahead.
Like x squared, pretending the x3 is just x.
Making the x to the power of 3, make that x?
Like pretend that it's x, and then having the square, so it's like x squared, and then on top it's x squared, so they're kind of non-zero.
I wouldn't make a substitution like that unless you're going to be able to keep track of stuff. So, but yeah. Okay. Oh, yes, question. What happened to the x squared? Which x squared? Yeah, the x squared got substituted out. So you see, okay, this is a good question. So the x squared dx, you see this? That got substituted for 1/3 du. Okay, let's take this one 30 seconds. Evaluate sine x minus cos x over cos x dx. Actually, I changed my mind. Sorry. We don't have enough time for this one. This is going to be homework. Because this is just a simple u sub, and then this is just going to be 1, integrating 1. So let's skip it. Is that okay? Sorry, everyone. Do we want to do this one? No, this will take too much time. Try this one as well. This sum. Okay, we're going to speed run some stuff really quick. Is that okay? So this sum, this is the sum from n is equal to 1 up to k of n cubed plus n. So you just use the formulas. So this is k squared, k plus 1 squared over 4. And this is k times k plus 1 over 2. Okay, we have 3 minutes. I want to get through 3 questions. Can we do 1 a minute? All right, so let's compute using a left Riemann sum, the area under the function f of x is equal to x squared plus 1 on the interval 0 to 4. So here, let's remember our definition of a Riemann integral. Let's say integral length tending towards 0. Towards 0. So we're integrating from 0 to 4 of our function. Remember, we're dividing this into infinitely small rectangles, which have length delta x and have height f of x at our sample point. So in this case, the integral of from 0 to 4 of f of x dx, this is equal to the limit as our delta x goes to 0. Now, that's the same as the number of rectangles going to infinity. We want now the width of our rectangle times the height of our rectangle, and we want to sum over all of our rectangles. So we're summing over from I is equal to 1 up to n. The width of our rectangle is going to be b minus a over the number of rectangles, so 4 minus 0 over the number of rectangles. And the height of our rectangle is going to be f of our original point A, which is 0, plus our width of our rectangle times I. So I times 4 minus 0 over n. So this is this part here, f. This is just going to be, so x squared plus 1. So it's going to be I times 4 over n squared plus 1. So this is our integral, our formal definition. The next question says, do the exact same thing but use indefinite integration. So we're going to go from 0 to 4 of x squared plus 1 dx, which is just x cubed plus x evaluated from 0 to 4, which is just 4 cubed plus 4 minus 0 minus 0. And then the final question, I want to thank Rose for giving the McMaster calculator. We're going to compute the exact same integral using our calculator. So we want to integrate x squared plus 1 from 0 to 4. So let's go over here. In order to do that, we're going to click Shift up here. We're going to click the integral. Oh, no, sorry, we're not going to click Shift. We're going to click the integral button. We're going to type x squared plus 1. Was it plus 1? X squared plus 1, comma, our left bound 0, comma, our right bound 4. And we're going to get our answer. And by the way, sorry, for the integral one, I forgot to divide by 3 in our x cubed computation. So everyone remember, if you don't know how to integrate, you can use our calculator. All right, so thank you so much. I'll post the test take-up, and good luck on Monday. I will. One sec, sorry. One sec, sorry. Thank you so much. Let's see. Have a good one.
How to do use calculator?
Oh, I don't have it. What?
Oh, my calculator, right?
Yes, if you're playing pool, it's okay. Yes.
Question.
Hi.
On your YouTube channel, if you have like a test 2 review thing, just like how you did for like test 1.
Oh, like a take up, yeah.
On test 1, you had like a review, like everything you need to know for like the test. Like
Oh, I don't have a summary. No, unfortunately. I made that one last year over reading week, and I don't have enough time this week. I've been super swamped. I'm sorry. But the stuff is on Child's Math, so. And I'll post a take-up of the midterm. I will do that. I'll put it on Teams in the channel. It'll probably be in the enrichment column. Yeah. You're on complex mode. So you click mode, and then mode 1, and now the integral works. There you go.
So you know closest, even, tangent, sine.
Yes.
Are there inverses the same?
Wait.
Ah.
Oh, damn.
So I'm going to leave that one to you to prove, but yes, it should be.